Today we're diving into a field that's all around us in modern medicine, but you might never even notice it. It's called medical physics. And really, it's the incredible story of how we took the fundamental laws of the universe, the same physics that explains stars and atoms, and figured out how to use them to see, inside, and even heal the human body.
So here's a question to kick things off. What could possibly connect a philosophical idea from the 1600s with the most advanced cancer treatments we have today? I mean, they seem like they're worlds apart, right? One is powdered wigs and early mechanics. The other is high-tech, cutting-edge medicine. But believe it or not, there's a powerful thread that ties them together.
And that thread is a truly radical idea that started centuries ago. It was the simple question, what if we could look at the human body with the same objective, mathematical rigor that we use in physics? What if we could turn the art of medicine into a science? That question, right there, changed absolutely everything.
Okay, so to really understand our world of MRI scanners and precision radiation, we've got to jump back in time, way back. We're going to the 17th century, to the exact moment when doctors and philosophers started looking at the human body in a completely new and kind of shocking way.
You have to understand what a monumental shift this was. For more than 1,000 years, medicine was all about the Galenic paradigm. It was this subjective art of balancing mysterious humors in the body. But then, a new philosophy called iatrophysics came along and made this wild claim. The body isn't governed by humors. It's governed by levers, fluids, and forces. It's not mysterious. It's a machine.
So how did a wild idea like that actually take hold? Well, it was kind of the perfect storm of three key breakthroughs. First, you have William Harvey, who figured out blood circulation and reframed the heart as just a mechanical pump. Then, the philosopher René Descartes came along and basically gave everyone philosophical permission to study the physical body like any other machine. And then there's Centaurio, who pioneered the idea that life itself could be measured. This guy famously spent decades sitting in a weighing chair, obsessively trying to turn life into hard data.
So, this idea of the body as a machine really set the stage for the next giant leap. Because if the body is just physics, then maybe we can use other kinds of physics to see it and fix it. The next breakthrough came when we learned how to harness forces that are completely invisible to the human eye. And once this started, things happened incredibly fast. In 1895, Runton discovers X-rays. For the first time ever, we could see inside the body without cutting it open. A game changer! Just 3 years later, the Curies isolate radium, which gave us the first tool for therapy. And by World War I, Marie Curie herself is driving mobile X-ray vans, her little Curies, to the front lines. Right from the very beginning, medical physics had this dual mission, to see the problem and to treat the problem.
But this incredible new power was dangerous. The early pioneers, both the doctors and their patients, had no idea what they were dealing with. They started suffering from terrible radiation burns and other injuries. They were wielding this amazing new tool, but they didn't understand the risks.
So, out of this danger, an urgent need was born. A need for safety, for control, for measurement. And this is what formalized the entire field of medical physics. The science of dosimetry, which is all about accurately measuring radiation dose, it wasn't just some technical exercise. It became a moral imperative to protect people from harm. Now, once physicists got serious about measuring and controlling radiation, it opened the door for the next big revolution. By the mid-20th century, we were developing technologies that could generate and aim radiation with energies and precision that were just completely unimaginable before. And the perfect example of this leap is the Medical Linear Accelerator, or LINAC for short. The first one was installed in 1956, and it completely changed the game. For the very first time, doctors could create powerful, high-energy beams that could reach tumors buried deep inside the body. It completely transformed radiotherapy. But even with this amazing tool, there was a fundamental problem. With standard X-ray therapy, the beam goes into the body, it hits the tumor, which is great, but then it keeps on going. It passes right through, delivering what's called an exit dose to all the healthy tissue and organs behind the tumor. It created a ton of unavoidable collateral damage.
And this is where particle therapy comes in. It's so clever. Instead of X-rays, it uses particles like protons. And here's the beautiful part. Protons can be programmed to travel to a very specific depth inside the body, dump almost all of their energy in one massive burst, that's the Bragg peak, and then they just stop, dead in their tracks. There's almost no exit dose. It's like having a physical stop sign for the radiation, which lets you spare healthy organs right behind the tumor.
So that relentless quest for precision brings us right up to today, where our ability to see and treat disease has gotten down to the molecular level. We're not just seeing organs anymore, we're seeing the actual pixels of the disease.
I mean, the imaging tech we have now is just astounding. A conventional CT is still the workhorse, it's fantastic. But then you have something like a photon-counting CT, which doesn't just see shapes, it gets spectral information. That means it can start to tell the chemical makeup of what it's seeing. And then you have 7 Tesla MRI. Look, if a standard MRI is like high-def TV, 7T is like jumping to 8K resolution. Surgeons can see the tiniest details with just breathtaking clarity.
So what do you do with all this incredible diagnostic power? Well, you pair it with an equally precise therapy. And that's the idea behind a new field called Theranostics. You basically fuse diagnosis and therapy into a single smart molecule that hunts down cancer cells and then delivers a tiny payload of medication or radiation right to their doorstep.
Physics here is just incredible. Some of these next-gen agents use isotopes that release something called Auger electrons. Now, these things are intensely destructive to cells, but, and this is the key, they have an extremely short range. We're talking nanometers, a few molecules wide. This means they can dump all of their cell-killing energy right next to a cancer cell's DNA without touching the healthy cell right next to it.
I love this quote from the source material. It captures the idea perfectly. These things are essentially tiny, tiny depth charges at the molecular level. They're designed for maximum destruction, but with microscopic precision. The level of control is just mind-boggling.
But all this amazing technology, these 8K images, this molecular targeting, it creates a brand new problem: overwhelming complexity. The amount of data is just staggering. And to manage it all, the next revolution in medical physics is already here.
You know, the sheer volume of data, the complexity of the treatment plans, the need to adapt on the fly, it's just too much for a person or even a team of people to handle anymore. AI isn't a cool new feature. It has become absolutely mandatory to make this kind of personalized medicine actually work. Here's a perfect example of what that looks like. It's called adaptive radiotherapy. The patient gets scanned every single day because tumors shrink and organs shift. And AI can look at that new scan, instantly outline everything, and then recalculate the perfect treatment plan for that day's anatomy, a task that would take a human physicist hours. The physicist's role then shifts. They become the expert who validates the AI's plan, making sure it's safe and effective before hitting the go button.
And looking ahead, this all brings some huge new challenges. The medical physicist's job is changing, from calibrating a machine to what you might call AI governance, making sure the complex software is safe and reliable. Brand new technologies like flash therapy that delivers radiation in milliseconds require entirely new physics just to measure them. And maybe the biggest question of all is, how do we make sure everyone has access to these incredible tools so we don't create a massive digital divide in healthcare?
And that really is the fundamental question for the future of this field. As our treatments rely more and more on algorithms, on simulations, on digital models of the patient, how do we keep it all grounded? The core mission of medical physics, going all the way back to the beginning, is to apply the real unshakable laws of the universe to make sure that every single treatment is not only effective but fundamentally safe and real.